Okay, recording has started. Remember last week we analyzed the evaluating properties of PVT relations as well as ideal gas model. Before that, we applied the first law of thermodynamics in closed systems. The first law of thermodynamics is the conservation of energy. This week, we will analyze the open systems in terms of analysis of first law of thermodynamics of conservation of energy. So let's first remember the difference between a closed system and open system. A closed system or control mass has no mass interaction at the boundary. So no mass can cross the boundary. However, for the case of open systems, or sometimes we can see the name of open system as control volume. Mass can cross the boundary. And in both systems, energy can cross the boundary. Let me do some corrections. Okay, these are the differences between two systems. In closed systems or control mass, no mass can cross the boundary, meaning that the mass inside the system is constant, whereas in the open systems, or in other words, the control volume, mass can cross the boundary. An example of an open system is seen here. The dashed lines represent the boundary of the system, of the open system. As you can see, at ground one, mass is crossing the boundary, and at exit, mass is crossing the boundary at the other side. So the net change within the boundary can be obtained from the difference of exiting boundary minus incoming boundary. So the difference between the two mass flows in and out of the system is going to be the net change within the system. So the net change within the system is obtained from incoming flow minus exiting flow. If we write it mathematically, we can set it as the net change in the mass inside the control volume is equal to incoming mass flow per unit time minus exiting mass flow per unit time. Remember, when you have a dot on something, it means it's per unit time or it's the rate of something. So m dot is the mass per unit time, or in other words, mass flow rate. Let me give you an example. Suppose there is a bathtub. If the bathtub is being filled at the rate of m dot in, and at the same time, if there is a discharge from the bathtub at the mass flow rate of m dot out, if they are the same, meaning if the mass flow rates of m dot in and m dot out are the same, you can see that the level of the water inside the bathtub will be the same. However, if m dot in is greater than m dot out, the level of the water will be increasing. Otherwise, if the m dot out is greater than m dot in, the level of the water will be decreasing. The change in the level inside the bathtub is represented by this. So it's the mass inside the control volume, mass time rate change of the mass inside the control volume, and it's equal to incoming mass minus exiting mass. If there are more than one inlet and more than one exits, you can write the net change within the control volume as the total incoming mass flow rates into the control mass minus the total exiting mass flow rates from the control volume. When there is only one inlet in one-dimensional form, for instance, a flow inside the pipe is a one-dimensional flow, the mass flow rate can be calculated from m dot equals rho, which is the density cross-sectional area of the pipe times velocity of flow, or because rho is 1 over specific volume, you can write it as AV times AV divided by V, or rho times AV. They are the same things. By the way, this AV is called volumetric flow rate. Whereas this mass end up is called mass flow rate. So when we say mass flow rate, we are talking about mass per unit time. And most of the time, the unit for mass flow rate is kilograms per second. On the other hand, the unit for volumetric flow rate is cubical meter per second. Suppose that we have an open system of a compressor connected to a pipeline. So there is a mass flow rate coming into the compressor and it goes out as it's compressed. Normally, the incoming mass should be equal to exiting mass because there is no accumulation of the mass inside here, so that dm over dt is 0. So in this case, we can say that incoming mass is equal to exiting mass. This happens in systems of steady state. Steady state is when the properties do not change with time. So when there is steady state, the left-hand side of the equation is 0. This is called steady state, meaning that there is no change of the mass inside the control volume with time. So if the level of the water inside this bathtub is constant, it doesn't change with time, then the mass inside the bathtub is the time rate of change of the mass of the water inside the bathtub is 0, meaning that the mass is constant. Then we have a situation in which the total mass incoming should be equal to total mass exiting. Most of the time, we will be dealing with steady state situations, not time-dependent situations. In time-dependent situations, we may have a situation in which dm dt may be non-zero, as in the case of the example of bathtub. So if the level of the water is increasing or decreasing, then it means that the time rate of change of the mass inside the bathtub is not 0. We have an example here. According to the example, a steam of 200 Celsius is mixed with a water of 40 Celsius, and they leave this system, the mixer room, as something else, some other temperature, we don't know. The pressures are same, they have to be same, otherwise there wouldn't be a flow as indicated here. So according to this, the water is mixed with the steam and comes out as something else. So we would like to find out the mass flow rate at exit 2. So we are going to find out the mass flow rate here, m dot 2, as well as the velocity at 3. So we are given the mass flow rate at 1, at mass flow 1. We don't know the mass flow rate at 2, and we don't know the mass flow rate at 3, but we are given the volumetric flow rate. According to the conservation of mass, at steady state, we have a situation at which the sum of the inlets must be equal to sum of the exits. So we have two inlets and one exit. It means that m dot plus m dot 1 plus m dot 2 is equal to m dot 3. This is required by the conservation of mass. It's steady state, so there is no change of the mass inside the control volume. So inside the control volume, mass is constant, so that the derivative of it is 0, meaning that it's steady state. Now we would like to find out the mass flow rate at the inlet 2 and the volume, the velocity at the exit 3. So we start with the mass flow rate equation. It's steady state, so there is no change within the control volume. It's 0. We have m dot 1 inlet plus m dot 2 another inlet minus m dot 3 exit. So sum of them is going to be 0. So that m2, m dot 2, the mass flow rate at inlet 2 can be found from m dot 3 minus m dot 1. M dot 3 can be written as the volumetric flow rate divided by V3 according to the definition made here. So m dot can be written as A times V, which is the volumetric flow rate, divided by the specific volume. So if we write the m dot 3 in terms of the given values, so m dot 3 is area of the exit 3 times the velocity of the exit divided by the specific volume of the mixture at the exit 3. So by using the given values, the inlet mass flow rate is given. It's given here 0.06 cubic meter per hour. So this is given, and the mass, the volumetric, the specific volume can be found from the table, because as you can see, the properties at the exits is given to you as 7 bar. So it's saturated liquid. You need to go to the saturated liquid table, saturated water table, and you need to read the value for specific volume, which is V3 is equal to V3 F, because it says it's saturated fluids, saturated liquid. So you need to use the saturated water table to find out the specific volume of the liquid at exit 3. So the value of the specific volume at the exit 3 is found to be 1.108 times 10 to the minus 3 cubical meter per kilogram. So by using this value, you find the mass flow rate at the exit 3 to be 54.15. You were given the mass flow rate at the inlet so that you can find the mass flow rate at the inlet 2. The mass flow rate at the inlet 2 is found to be 14.15. Because the mass flow rate at the inlet can also be written as area 2 times velocity 2 divided by the specific volume at 2. Then velocity at the inlet 2 can be found from m dot 2 times v2 divided by area of the 2. It's a compressed liquid at 40 Celsius. So the specific volume of the compressed liquid can be found as V2 is approximately equal to V2 at 40 Celsius. Remember that the properties for liquids, the subcooled liquids, can be approximated as the saturated liquid property at the saturation temperature. So the temperature is given as 40. We can take the specific volume of the liquid at 40 Celsius saturation temperature approximately as the specific volume of the compressed liquid. So by using this compressed liquid value, we can calculate the velocity at the inlet 2, which is found to be 5.7 meters per second. So in this example, we use the principle of conservation of equation, conservation of mass, and it was a steady state situation so that the mass flow rate, the time rate change of the mass inside the control volume is 0, so that the sum of the incoming masses must be equal to sum of the exiting masses, and this is only valid for steady state. So this is valid only for steady state, where dm dt is 0. The explanation of conservation of mass is very clear. According to the mass conservation, what comes in must go out if it's not accumulated inside. It's very logical to understand. And we have a similar situation for the energy flow in and out of the system. So suppose that we have a control volume like this, an open system. A mass flow rate of m dot in comes in, another mass flow rate of m dot exit is leaving. And because the mass can also carry energy in terms of internal energy, kinetic energy, and potential energy, so not only do we have work and Q in and out of the system, as in the case of closed systems, but also we have the energy carried by the mass flow rates. So for closed systems, we have only the energy interaction. We have only the energy interaction as Q minus work, which is equal to the net change in the internal energy plus the change in the kinetic energy plus the change in the potential energy. But in open systems, we also have the effect of the energy carried by the mass as kinetic potential and internal energies. So this effect is shown here as the energy carried by the mass. So energy carried into the system is m dot times U inlet, the internal energy of the inlet incoming fluid, the kinetic energy of the incoming fluid times the potential energy of the incoming fluid minus m dot exit, the exiting energy, total energy, internal kinetic plus potential, and of course, as in the case of closed systems, we may have interactions of Q and W. So these things are additional because of the mass flow rate. If you are considering the time rate of change of the total energy content within the system, you can take the time derivative of the energy. So the total rate of change of the energy inside the system is equal to Q dot, which is the energy added by or removed by heat per unit time, minus W dot, work added or removed per unit time. By the time W dot is power, as you remember, then we have the energy term due to the streams of fluid incoming and exiting. Sometimes it's better to separate the work as flow work plus the work due to boundary work, electrical work, and so forth. So if we separate the work as the work per unit time inside the control volume, which can be the boundary work or electrical work or another kind of work, then we have the work due to the pressure at the inlet minus work due to the pressure at the exit. Remember, when we say W dot in mechanical sense is force times velocity, and force is the pressure force here. So P times area is the pressure force. So this whole thing is the work per unit time due to the pressure at the inlet minus the pressure work or pressure force per unit time, pressure work per unit time at the exit is going to be the net work due to the pressure. And also, as I said, we may have other types of work as electrical, boundary, and others can also be exist, etc. So if we combine the work under boundary under the work of the control volume plus the work at the boundaries due to the pressure, then we have a situation in which the total work is composed of work done in the boundary, done in the control work as electrical boundary as well as etc. Plus the pressure work due to the mass flow rate at the inlet minus pressure work at the exit due to the mass flow rate, because A times V here, A times V here can be written as N dot times specific volume. So this work per unit time can also be written as N dot times pressure times specific volume. So we will be writing this work term here, the work term here, separately as shown here. So when we do this, when we write the work term separately, as the work due to the electrical work and or the boundary work and so forth. And this part is separated from the total work. This is the work due to the pressure work at the boundaries, at the inlet and at the exit. And remember that we have a combination property called enthalpy. If the internal energy and pressure work is combined in one term as enthalpy, then the time rate of change of the energy inside the control volume can be written as Q dot CV minus W dot CV plus N dot enthalpy plus kinetic energy plus potential energy at the inlet minus N dot times enthalpy plus potential kinetic plus potential energy at the exit. So this is the net energy due to the flow of the streams. One is carried into the control volume, the other is carried out of the control volume. So the net change is going to give you the change due to the change of the energy inside the control volume per unit time. If there are more than one inlet and exits, we can write this equation with summation sign. So if you have n number of inlets and n number of exits, you can write the total incoming energies under summation sign and total exiting energies under summation sign as well. Most of the time, we have situations where the system is run at steady state. So when there is a steady state, dE dt, the energy content of the control volume per unit time is 0 if we are given a steady state situation. If we are given a steady state situation, the left-hand side of the equation is 0. So what happens if the left-hand side is 0? Then we can write the equation as 0, the left-hand side of the equation d dt is equal to net Q per unit time in and out of the control volume, net W per unit time in and out of the control volume, net flow of energy into the control volume as enthalpy, kinetic energy, potential energy, and the net flow out of the control volume as enthalpy, kinetic, and potential energies. And because of the steady state, the sum of the inlet masses per unit time should be equal to sum of the exit masses per unit time. So we can show this equation as Q and W collected at different sides. So if Q is on the left-hand side, Q plus the incoming energy must be equal to W plus exiting energy. This is the same equation here, written in another form. If there is only one inlet and one exit, then we do not have to use the summation sign. So by doing this, if there is only one inlet and one exit, the net Q and W and energy of the energy stream in and out of the system change per unit time is going to be 0 because it's steady state. Then we can write the whole thing as per unit mass because these are given in kilojoules per second, for instance. So the first term here, Q dot is, for instance, is in kilojoules per second because it's the energy per unit time. So if it's divided by N, so Q dot divided by N dot is going to give you kilojoules per kilogram. So in this form, it's not a rate form anymore. The time has gone. So it's the energy per unit mass. So if you divide the whole terms of this energy equation by m dot, you get energy per unit mass. So Q dot divided by m dot is small case q, which is kilojoules per kilogram. So this is small case q. And w dot divided by m is the small case w. And you have the differences of enthalpy, kinetic energy, and potential energy. This is called the steady state energy equation for an open system. So where can we utilize the energy equation for open systems in steady state? We have different applications of energy equation for open systems. The most basic one is the nozzle or diffuser. What's a nozzle or diffuser? A nozzle is used to increase the speed of the stream overflow. So as the area is decreasing, just take a look at this. If the area is decreasing, then we understand that there has to be an increase in velocity, because if, for instance, rho is constant, we have a situation called conservation of mass. So we have rho1, A1, B1, which equals to rho2, A2, B2. If it's incompressible, if it's liquid, meaning that the density does not change, we can set the densities to be equal. So this is incompressible. So from here, you can understand that if the area is getting smaller, then the velocity must increase. So if area is reducing, then the velocity must increase. This is required by the conservation of mass. Increase. This is required by the conservation of mass. When the velocity increases, according to the conservation of energy equation, suppose that there is no heat interaction with the surrounding, no work is done here. We have no change with the elevation, meaning that the potential energy is constant, so that the change in the enthalpy is equal to change in the kinetic energies. So because the kinetic energy is increasing, it requires that the enthalpy must be decreasing. In the enthalpy, you remember that you have U plus PV. So enthalpy is equal to U plus PV. If the temperature is constant, the change in the internal energy becomes zero. So it means that when area gets smaller, velocity must increase. Meanwhile, pressure must decrease in order to satisfy the energy equation. So this is the first one is required by the conservation of energy, and this is required by the conservation of the first one is required by the conservation of mass. The second one is required by the conservation of energy. This is called a nozzle, and a nozzle is used to increase the speed overflow. So by reducing the cross section, it's possible to increase the flow of a fluid, whether it's gas or liquid. The opposite of a nozzle is a diffuser, in which, as you can see, the exit area is greater than the inlet area, which means as area becomes greater, then velocity must be smaller, which requires, according to the conservation of energy, pressure must increase. So there are two uh, applications of the cross-section area reduction or increasing. If the cross-section is decreasing, it's called a nozzle. If the cross-section is increasing, it's called a diffuser. The application of nozzles and diffusers are various. For instance, one of the application is a wind test tunnel facility. This is a wind test tunnel in which, for instance, a drag coefficient on a car, whether it can be a prototype or a small model, is measured. There was an example regarding the friction force or the drag force on bicycle. Remember that the drag force is calculated from the drag coefficient times area times rho v squared divided by 2. You can see the example of a cycle, this bicycle. So if in this wind tunnel, you know the velocity of the flow, you can measure the drag force on this car. So from the drag force and the velocity, you can calculate the drag coefficient of the car. This is done all the time for the cars manufactured in manufacturing plants. In order to obtain a high velocity of the flow on the car, because at the inlet you cannot have a velocity as high as the velocity of a car on the road. So suppose that the velocity on the car on the road is, let's say, 100 kilometers per hour. It's approximately 27 meters per second. Because the fan cannot deliver 27 meters per second, by using a nozzle like this, we can accelerate the speed of the air to 27 meters per second. And after it passes through the section, test section, we have to decelerate it because we do not want that much speed at the exit. So in order to decelerate it, in order to slow down the exit of the air, we may have a diffuser. So a wind tunnel is basically comprised of both a nozzle and a diffuser. If you write the conservation of mass and conservation of energy equations for this nozzle or diffuser, we obtain, because it's steady state, the mass flow rate, the mass inside the control volume does not change, so it's constant. dmdt is 0. And also the energy content is constant because it's steady state. So in both cases, we have 0 on the left-hand side, both mass equation and energy equation. So the first one gives you incoming mass being equal to exiting mass. What comes in should go out. In the second one, the energy equation gives you the net Q in and out of the system per unit time minus net work in and out of the system per unit time plus the net energy carried into the system as enthalpy plus kinetic energy plus potential energy and net energy exiting the system as enthalpy plus kinetic plus potential energies. So if we rearrange this equation, we get is another equation in which the left-hand side is 0, Q interaction, the enthalpy change of the incoming and exiting air plus kinetic energy change of the incoming and exiting air, because there is no change in the elevation, so that the potential energy does not change. And because there is no work done on the system, we can take W dot to be 0. So we only have the heat interaction with the surrounding. It may lose heat or it may gain heat. The change in the enthalpy plus change in the potential energy, kinetic energy. Most of the time, these tunnels are well insulated so that we can also drop this term. And in this case, the enthalpy change at the inlet and exit is going to be equal to kinetic energy change at the inlet and exit. There's an example regarding this. So according to this example, a steam nozzle, which is given here, has a inlet pressure of 40 bars, 400 Celsius, and 10 meters per second. This is for sure superheated steam. If we check it on the table, this is superheated steam. Then after it passes through the nozzle, in the nozzle, you remember that velocity increases while pressure decreases. And it's asking the exit area necessary for this nozzle. So we have a pressure of 15 bar at the exit. As you can see, the pressure has gone from 40 to 15. And also, inlet velocity and exit velocities are given. Exit velocity is much higher than the inlet velocity, which is expected because it's a nozzle. So if you put everything on the saturation curve, we have initially 40 bar. So initial situation is this. We have steam at 40 bar and 400 Celsius. When it passes through the nozzle, the final pressure is 15, and the final temperature is not given, but we know that its pressure has dropped from 40 bars to 15 bars. Because it's expanding, you can see that the specific volume must increase. So outlet condition is also superheated. You have superheated steam at the inlet, also superheated steam at the exit as well. So we're going to find the exit velocity here. The first thing to start with is to find out the mass flow rate, because the mass flow rate is found from m dot times V2 divided by this small case v is the specific volume, and capital case V is the velocity at the exit. So this is how we're going to calculate the exit area. But in order to do this, we need to find out the value for the specific volume at the exit. This is unknown for the time being. Let's write the energy equation. Because it's steady state, the left-hand side is 0. And it says that the nozzle is well insulated. Well insulated means that there is no heat interaction between the surrounding. So Q dot is 0. It's insulated. This is because it's insulated. And because there is no work interaction, work dot W dot is also 0. So we have a situation where we have 0 on the left hand side, Q dot is 0, W dot is 0. All we have is N dot times the total energy of the incoming stream, enthalpy, kinetic, and potential energy, minus the total energy of the exiting stream, enthalpy, kinetic, and potential energies. If you look at this nozzle, you can see that the elevation does not change. It's parallel to the ground, so there is no change in the potential energy. So we can also cancel the potential energy terms. Then all we are left with is the enthalpy terms and kinetic energy terms. So the exit enthalpy can be found from H2 is equal to H1 plus the change in the kinetic energy. And H2 is found from the values of H1. And because H1 is a steam at 40 Celsius and 40 bars and 400 Celsius, you can use this steam table and find the value of H1. So once you find the value of H1, you can use it inside this equation to find the value of H2. The value of H2 is 2992.5. This is the calculated value. So you need to go to the table, and with this H2 and the pressure 15 bar, H2 and the pressure 15 bars, you can go to the superheat table and find the value of V2 here. Once you find the V2, you can calculate the area at the exit, which is 4.89 times 10 to the minus 4 square meter. So it's enough to know the specific volume to calculate the area if you are given the mass flow rate as well as the velocity. Do we have any questions so far? Okay, let's have a break of 10 minutes and we'll be back at 2 o'clock. Recording has started. The devices with a single inlet and single exit are called single stream devices, and the most basic one of single stream devices are nozzles and diffusers. Nozzles and diffusers are used to increase the speed of a flow or decrease the speed of it. The second type of single stream device is a turbine. In a turbine, as the kinetic energy of the flow is decreased, work is obtained. So the energy of the incoming stream, the kinetic energy of the incoming stream, or sometimes the potential of enthalpy of the incoming stream is converted to work. So examples of turbines are vapor turbines used in the vapor power plants, turbines in gas turbine plants, and aircraft engines. And as you can imagine, as the kinetic energy is converted to work, we have pressure becoming lower as the flow expands into a larger volume. Another type of turbine is an hydraulic turbine. So in a hydraulic turbine, the potential energy at the inlet is converted to work, very similar to the top one, but at the top one, the kinetic energy is converted to work, while in this bottom one, the potential energy at the inlet is converted to work. This is a hydraulic turbine used in a hydroelectric plant, and inside the hydroelectric plant, there is a mass of water, a height of water, which has a potential energy, like in a dam. So as the water flows through the turbine, the potential energy is converted to work. And in this case, work is obtained by the reduction of potential energy versus the reduction of the kinetic energies here. An example is given for a turbine. Steam enters this turbine at 60 bars 400 Celsius with a flow rate of 4,600 kilograms per hour, and the inlet velocity is 10 meters per second. As it expands through the turbine, it delivers a power of 1,000 kilowatts. So it's asking the heat transfer rate between the turbine and the surrounding. So it doesn't say an insulated turbine, so we have to calculate the heat transaction between the turbine and the surrounding. We are going to calculate the heat loss from the turbine. And the exit conditions are: the exit pressure is 0.1 bar atmospheric pressure. The exit steam quality is 90%, meaning that whereas in the beginning it was superheated, now at the exit it's a mixture because it has a quality of 90%. It's less than 1. And also the exit velocity is given. So if you look at the TV diagram, the initial pressure is 60 bars. So this is the initial pressure curve. And the temperature is given as 400 Celsius. And this location is for sure superheated. And as it expands through the turbine, the pressure drops to 0.1 bar. It's given. And because exit quality is 0.9, we understand that it's in a region which we call mixture, because the quality is less than 1. It's not saturated or it's not superheated. It's a mixture. So first we can start with the energy equation, the conservation of energy, because it's steady state. The left-hand side is 0. We have Q transaction with the surrounding. The problem is saying so. We have work output because it's a turbine, it delivers work. We have a total energy of the stream, which is consisted of enthalpy of the incoming steam, the kinetic energy of the incoming steam, plus the potential energy of the incoming steam, minus the total energy exiting the turbine, so that we can calculate the heat transaction with the turbine and the surrounding as work plus the net energy incoming to the system and exiting the system. Of course, we have to have the values for H1, H2. The velocities are given. There is no problem with the velocities, but we have to find the value for H2 from superheat table and the value for the H1 from saturation table. Of course, it has a quality, so that the quality must also be considered when the calculation is done. So the enthalpy for the exit is HF2 plus X2 times the difference of the gas enthalpy minus liquid enthalpy. Remember that we had a general equation. A general property is equal to property of the fluid plus the quality of the steam times the property of the gas minus the property of the fluid. So in this case, the property is enthalpy, so we can calculate enthalpy at the exit, so that the enthalpy difference here is found to be minus 831. Why minus? Because as the steam expands from a high velocity to low velocity, or high enthalpy to low enthalpy, its enthalpy is decreased because it's converted to work. At the same time, there is a reduction in kinetic energy, and this reduction of kinetic energy is just 1.2 kilojoules per kilogram. As you can see, if you compare these two values, the reduction or the change in the kinetic energy can be taken as negligible most of the time, because it's much smaller than the change in the enthalpy. In any case, you can include it in the calculations. So this is the change in the enthalpy part, change in the kinetic energy part. This is the work, because you have to have the work term here, and it's going to be the work delivered by the turbine. So you find that the turbine is losing 61 kilowatts. If it was perfectly insulated, then this would be zero, meaning that you could have more work. But in this case, because the turbine is losing heat, the total work acquired by this turbine is less. Other single-stream devices can be compressors and pumps, whereas the turbine is used to obtain work by expanding a fluid. In the compressors and pumps, fluid is pressurized. So the reason why we use a compressor or pump is to increase its pressure. If it's a gas, the device used is compressor. So in the case of a gas, we use the term compressor, or we use the device compressor. If it's liquid, we use a device called pump. So if you want to increase the pressure of, for instance, air, you need to use a compressor. Otherwise, if you want to pressurize water, for instance, you need to use a pump. But in both cases, the objective of the device here to increase the pressure of it. There can be several kinds of compressors. For instance, the first type shown here is the reciprocating compressor. It looks like an internal combustion engine. It has a piston that moves back and forth. So as the piston goes down, an inlet valve is opened, so air comes in or gas comes in. As the piston goes down, this inlet valve is closed and exit valve is open, so the pressurized air leaves the compressor. Another type of compressor is a rotating compressor, such as this one. it looks like a turbine, but inverse of a turbine, because as you can see here, the volume is decreasing, and the shaft of the compressor is delivered a work, whereas in the turbine, the shaft delivers a work. So we have to put work in the shaft of a compressor, whereas in the case of a turbine, the turbine delivers work. Here, in the case of a turbine, turbine delivers work. So this is called an axial turbine because the flow of the gas is axial compressor, sorry. Another type of compressor can be a centrifugal compressor, which uses the principle of transferring of angular momentum. So this uses the principle of transfer of angular momentum, but the first one uses the principle of decreasing of the volume. So as the volume is decreased, the pressure is increased. And the final one is another compressor. The compressors are basically two types. One of them is positive displacement compressor. So this one and this one are positive displacement because they use the principle of compressing the fluid by reducing the volume of it. But this type is called dynamic. The centrifugal compressor is called dynamic because it uses the principle of angular momentum transfer. But whichever the principle is, the objective of a compressor is to increase the pressure of a fluid by adding work on its shaft. An example of a compressor is given here. An air compressor has inlet properties of 1 bar, 290 Kelvin, 6 meters per second of airflow, and inlet area is 0.1 square meter. Because the objective of a compressor is to increase the pressure of the air, as you can see, P1 is increased to P2. Initially it was 1 bar, now it's 7 bar. And due to the compression, the temperature of the air increases because according to the ideal gas law, you remember that there is a relationship between the pressure and temperature of the air. So at the end of the compression, you should expect that not only the pressure but also the temperature will increase. So we always start with the general energy of the conservation of energy, general equation of conservation of energy, because it's steady state, the left hand side is 0. So this is 0 because it's steady state. So this one is 0 because it's steady state. The compressor is not perfectly insulated, so there is heat interaction between the surrounding. We have to provide work to the shaft of the compressor, otherwise it won't work. Then we have the total energy in the incoming stream plus the total energy at the exiting stream. So the work can be written as QCV plus the net enthalpy and net kinetic energy, because we may assume that there is no elevation difference in the compressor, because as you can see, the air leaves the compressor at the same elevation, meaning that there is no change in the potential energy. So we just need to calculate the values first. M dot is, as you remember, A times V divided by V dot, V, according to the ideal gas law. PV is equal to RT. So you can find the V as RT divided by T. A is given, the inlet area is given, inlet velocity is given, inlet pressure is given, so that you can calculate the m dot, and m dot is the same at the inlet and at the exit. This is constant because it's steady state. So the work can be calculated with the given values, as this is the heat loss given to you, because in the statement of the problem it says that there's a loss of heat of 180 kilojoules per minute. So this is the amount of heat loss per unit time. So we need to put it as minus 100 kilojoules per minute. By dividing it by 60, we can find it in kilojoules per second, which is kilowatts. Then we have to use the change in enthalpies. The change in enthalpies can be found from the air table, because this is an air compressor. So we have 290 Kelvin. From the table we find 290.16 kilojoules per kilogram of enthalpy, specific enthalpy. At the exit we have 450, and from the table again we find the enthalpy per unit kilogram to be 451.8 kilojoules per kilogram. We just put everything in this equation to find the work necessary to operate this compressor. So the work necessary to operate this compressor is minus 119 kilowatts or kilojoules per second. The reason why we have minus sign, remember that in a system, if work is done on a system, it's minus work. If the system does work on the surrounding, it's a plus work. If there is a Q incoming to the system, it's a plus Q. If Q is removed from the system, it's a minus Q. So that's why we have minus sign here for the Q and minus sign for the work. There is something interesting here. The loss Q is minus 3 kilojoules. So it increases the work necessary, because if it was a perfectly insulated compressor, this work required to operate this compressor would be 3 kilowatts less than this amount. So as you can see, the heat loss requires that we have to put more work into the compressor to get the same kind of mass flow rate or pressure increase. There are other kinds of single stream devices. One of them, for instance, heat exchangers. Heat exchangers are devices that transfer energy, heat energy, from one fluid to another fluid. There can be several types of heat exchangers. For instance, the first one is direct contact heat exchanger, because in this heat exchanger type, let's say hot fluid and cold fluid are mixed together to get warm fluid. Let's suppose this is hot, this one is cold, and they are mixed to get, let's say, warm fluid. A very basic type of heat exchanger, and this type is called direct contact heat exchanger, in which both streams of hot and cold fluid are mixed together. However, mostly the fluids do not mix in the heat exchangers. We may have tube within a tube or concentric tube. Sometimes they are called concentric tube heat exchangers, because we have two concentric tubes, one inside the other one, and one of the fluids may flow in this direction, while the other fluid may flow in the opposite direction. This one is called the counterflow heat exchanger. It's also possible to have the flow of the fluids in same direction as this one. So in this case, this one is called parallel heat exchanger, because both fluids are flowing in parallel direction. It's also possible to have the fluids flowing in cross direction. So as you can see, one flow is flowing in this direction, whereas the other one flow is flowing in this direction, whereas the other stream flows in the perpendicular direction. You can see heat exchanges of cross-flow heat exchangers in car radiators. In car radiators, where the engine water is cooled, the engine water that gets into the radiator is cooled by the air coming from the in front of the car. So air and water flows in perpendicular direction. That's why they are called cross-flow heat exchangers. But at the end, whatever the type of the heat exchanger, the objective or the purpose of the heat exchanger is to transfer heat from a hot fluid to cold fluid. An example of a heat exchanger is given here. In this example, steam of 0.1 bar and quality of 95% is condensed to liquid of 0.1 bar and 45 Celsius. It's subcooled. Why? Because normally, if it was saturated, the saturation temperature would be 100 Celsius, because the pressure is 1 atmosphere. But it's cooled down below the saturation temperature, so the temperature here is 45. So in order to condensate the steam with a 95% quality to subcooled liquid at 45 Celsius, some amount of cooling water coming into the system at 20 Celsius and leaving at 35 Celsius is used. So the steam comes in as 95% quality and goes at 45 Celsius of liquid, goes out at 45 Celsius of liquid. However, cooling water, it gets in at 20 Celsius and goes out at 35 Celsius. It's logical to think that the heat exchange between them should be equal to each other. This is very reasonable to see, but we're going to do this by using the energy equation. In the second part of the equation of the problem, we are going to take the system as only the cooling water, whereas in the first part, the whole heat exchanger is taken as the system. So in the first part, the open system has two inlets, the steam inlet, cooling water inlet, and two exits, the condensate exit and cooling water exit. However, in the second one, the system has only the steam part. So in the steam part, there is only one inlet and one exit, but there is also the Q interaction between the two systems. However, in the first one, there is no Q interaction in total because the Q lost by the first system is equal to Q gained by the second system, so they cancel each other. However, in the second part, if you take the system to be only the steam part, then you need to consider the heat loss to the second system, which is the cooling system. So for the steam part, we have a conservation of mass, which is M1 is equal to M2. And for the cooling water, we have also another conservation of mass, which is M3 is equal to M4. How about the conservation of energy? In order to write the conservation of energy, we have to consider the work, the Q, also the total energy carried by the streams. So the left-hand side is 0 because it's a steady-state system. QCV, the net Q in CV, the net work in CV, the total energy carried by the steam into the CV, control volume, the net energy carried by the cooling water into the stream, into the control volume, the net energy carried from the system in the steam part, and the net energy carried from the cooling water from the steam part. Because the heat exchange is between the cold stream and hot stream, there is no heat exchange with the stream, with the system and the surroundings. So this one is 0 because there is no heat exchange with the surrounding. So we should say that in this case, Q is 0. Similarly, we have no work interaction, meaning that Q also, W is also 0. We can assume that velocities do not change, so V1 cancels this one, V3 cancels that one. The change in potential energies are negligible. So all we are left with is the change in the enthalpies. So this first part is the enthalpy change in the steam. And the second part is the enthalpy change in the cooling water. So from here we can write the ratio of the cooling water mass flow rate to the mass flow rate of the steam. The ratio of the mass flow rate of the cooling water to the mass flow rate of the steam is H1 minus H2 divided by H4 minus H3. If you look at the graph again, the state 1 is a mixture, so that we can calculate the enthalpy of the mixture as H1 is equal to H1F plus X1 times H1 gas minus H1 fluid. And these values are going to be obtained from the table of the steam at a pressure of 0.1 bar. So when we do this, we can find the enthalpy of state 1 to be 1465. And enthalpy of the water can directly be found to be water table as approximately to the enthalpies of saturated liquid. So remember that the enthalpy of the compressed liquid is approximately equal to the saturated liquid enthalpy given at this temperature. And similarly, the enthalpy of the water, cooling water exiting the system, can be approximated as the enthalpy of the saturated liquid at this given temperature. So if you use the enthalpies obtained from the table, we see an interesting result that the mass flow rate of the water must be 36 times the mass flow rate of the steam. It's very important. In order to condensate 1 kilogram of steam, it's necessary to use 36.3 kilograms of cooling water. So this is the which is very interesting. In the second part, if you take the system as the steam section only, then of course the left hand side is 0 because this is a steady state system. There is no work done. We can neglect the change in kinetic energy, no change in the potential energy, but there is a heat interaction between the steam part and the cooling part. If you calculate this, you found that the Q transferred to the cooling water is minus 2276.7, which means it's necessary to remove from the steam this much energy, this much heat, in order to convert this steam, mixture steam, to subcooled liquid. And it's actually the same value which is obtained by the cooling water. So you can write a similar equation for the cooling water as if you take the cooling water as the control volume, so cooling part is taken as the control volume here, then you can write the cooling water is taken as the control volume here. Then you can write the cooling water control part Q to be M3 dot, which is the mass flow rate of the water, times H4 minus H3. And if you calculate this, you will see that it's exactly this amount, 2267.76.7, but with a plus sign, because in this case, the cooling part gains this amount of heat energy, whereas in the heating part or in the steam part, the steam part of the heat exchanger loses this much of energy, and it's equal to the energy gained by the cooling part. In this example, we are given an electronic system which needs to be cooled. So we used a cooling fan. Air comes into the system. This could be a computer case. Air comes to the computer case at 20 Celsius, 1 atmosphere, and because of the noise considerations, it's necessary to keep the velocity of the incoming air to be less than 1.3 meters per second. So this is one criterion. The air incoming velocity must be less than 1.3 meters per second. And also it says that the exit air temperature should be less than 32 Celsius. So these are the design criteria. According to the design criteria, we have to choose a fan inlet which satisfies these two criteria. It also says that the electronic components inside consumes 80 watts. So these electronic components consumes 80 watts, and the fan consumes 18 watts. So these are actually the electric work put into the system. So in order to find the necessary inlet diameter of the fan, we should be using this formula. According to this formula, the mass flow rate of the air, which is constant because it's a steady state system, the incoming mass flow rate must be equal to exiting mass flow rate times the specific volume in the inlet divided by velocity in the inlet. The velocity is given to you. It should be less than 1.3 meters per second. And also we have the conservation of energy formula for steady state. That's why its left-hand side is 0. The computer case is well insulated, so there is no heat interaction between the case and the surrounding. This is 0. Work as electrical work is put into the system. Some part of the electrical work is because of the electrical consumption of the electrical circuits, and some part of the electrical circuit is because of the electrical work put in the fan. So we have a total electrical work of 80 plus 18. So this is 80 plus 18. Then we have the energy flow in and out of the system. The net change of the stream as energy is the enthalpy change, the kinetic and potential energy changes. We can assume that the change in the kinetic and potential energies can be neglected, so that we have the final appearance of the energy equation to be 0 being equal to minus WCV, which is the total electrical work, 80 plus 18, plus the change in the enthalpy. So from here we can obtain the m dot. Until now we don't know what m dot is, the mass flow rate of the air for cooling. M dot can be written in terms of work and in terms of enthalpy, because remember that enthalpy change is Cp times delta T from last week. So this is the enthalpy change. And also, m dot is equal to rho times A times V. So if you combine everything in this equation, you can use m dot as rho times AV. D1 is also 1 over rho. So by combining everything in this equation, you get a relationship between the inlet area and other values. And these other values consist of inlet velocity, which must be less than 1.3 meters per second. The work, electrical work, which is the electrical consumption of the electrical circuits, 80 watts, plus the electrical consumption of the fan, 18 watts. Then we have the exit temperature, which must be less than 32. It's also given to you. And inlet temperature is given. Also, all others are given. So by using the given values, you calculate the inlet area of 0.005 square meter. If you say that it's a circular inlet, so area 1 is pi d squared, d1 squared divided by 4. So you find the inlet diameter to be greater than 8 centimeter. It must be greater than 8 centimeter so that inlet velocity can be less than 1.3 meters per second. So the fan inlet must be at least 8 centimeters to meet the criteria given at the statement of the question. Do you have any questions regarding this example? Okay, let's move then. Another type of single stream device is a throttling device. Sometimes they can be called as expansion valves, because in a throttling device, the pressure is reduced substantially due to the narrow passages like this, or due to the porous plugs. When flow takes place inside a throttling device, we know that pressure goes down substantially. And actually, in this process, we have a situation where enthalpy does not change. The reason why enthalpy does not change is because of the energy equation. If you write the energy equation for this throttling device, you assume that the throttling device does not exchange heat with the surrounding. It doesn't do any work with the surrounding. The kinetic and potential energies does not change, so that enthalpies remain the same. When enthalpy remains the same, we should understand that U plus PV must be same, because enthalpy is a combination property as U plus PV. So if U plus PV is constant, and if P goes down while the V increases because it expands, it's called expansion valve, we understand that U must be go down also, because V increases, the volume increases, pressure decreases, then U must go down. U, as you remember, is CV times temperature. So when U goes down, the temperature also goes down. So what happens in an expansion valve or a throttling device is pressure is reduced, volume is increased because there is an expansion, but at the same time, temperature is reduced. This is why expansion valves or throttling devices are used in the application of refrigeration. In a refrigeration system, we will see the refrigeration system later, as the liquid in high pressure is throttled or is expanded through a throttling device, its pressure goes down drastically while it expands, and also the temperature becomes much smaller with respect to the inlet. So if the temperature becomes much smaller, it means that the refrigeration or the cooling has already started, and it continues in the part of the system, the refrigerating system, called evaporator. But it initiates the evaporator, it initiates the cooling by expanding the liquid into low pressure, where it expands and actually it starts to evaporate. And during the evaporation, it absorbs heat from the surrounding, meaning that it starts cooling the surrounding. There's an example regarding the throttling devices, but we will solve the example in the next period. Do we have any questions? So in this example, there is a special device to measure the quality of a flowing steam. So we would like to measure the quality of the steam that flows through this pipe. It's a steam with some quality, meaning that it's in the mixture zone. The pressure of it is given as 2065 kilopascals, and in order to measure the quality of the steam, a throttling device is used. So this high pressure steam is passed through this throttling device. As it passes through the throttling device, we know that it will expand to a lower pressure. But in throttling devices, we know that enthalpy remains the same. So even though pressure goes down, we know that enthalpy remains the same. So this is represented in this saturation curve. As you can see, the initial pressure is 2065 kilopascals, and it expands to atmospheric pressure, which is 101 kilopascals. Because it expands to a lower pressure, it becomes superheated. Initially, it was mixture, and when it expands to lower pressure, it becomes superheated. So we are going to find the quality of the steam inside this pipe as the steam flows downward. The first thing to do is to find the way to calculate the mixture enthalpy. Remember that mixture enthalpy can be written as fluid enthalpy plus the quality times the enthalpy difference between the liquid and the gas. So from here, we obtain the enthalpy, the quality as this equation. Because this is a steam in the mixture zone and the expansion steam is in the superheated zone, we can calculate the values of the enthalpies at the steams, at the expansion, and at the inlet. So at the inlet, we have 2065 bars, and if you use the saturation table, you will find H1F is 901 kilojoules per kilogram, and H gas 1 is 2800 kilojoules per kilogram. They are the values in the saturation curves as this one and that one, but our sample is here, so we have to calculate X. At the exit, we have atmospheric pressure, a lower pressure. So by using the exit steam temperature, which is given to you, exit steam temperature is given to you, and if you use the exit pressure, you can find the enthalpy of the exit temperature of the exit steam. So by using the enthalpies of the inlet steam and exit steam, you can calculate the quality of the steam inside the pipe. So the quality of the steam inside the pipe is found to be almost 96%. Up to now, we talked about many single stream devices such as nozzles and compressors, diffusers, pumps, turbines, heat exchangers, and these devices are actually used in system integration. For instance, this is an example system integration used in a steam plant. It's actually called a steam cycle. We will call it later Rankine cycle. In the Rankine cycle, we have basically four single stream devices. The first single stream device is a pump. The second stream device is a heat exchanger by the name boiler. The third single stream device is a turbine which delivers work. And the final single stream device is another heat exchanger which is called a condenser. So what happens is, as this pump delivers high pressure water into the boiler, it becomes steam inside the boiler. The steam leaves the boiler, enters the turbine, and as it expands through the turbine, it delivers work. At the exit of the turbine, because it has expanded, it has a much lower pressure than the inlet, but also, even though at the inlet it's superheated, at the exit it's a mixture. However, this mixture should be converted to liquid before it's pumped back into the boiler. So inside the condenser, this mixture is cooled by cooling water to convert it from water vapor mixture to liquid. So you have saturated liquid here at the exit of the condenser, and at the exit of the pump, you have compressed liquid. And this compressed liquid leaves the boiler as superheated vapor, and it becomes a complete cycle. So the purpose of the cycle is to deliver work, and this work can drive a generator or a shaft of a ship propeller, for instance. It's a power plant which uses steam, the water vapor, to deliver power in the form of mechanical energy from the turbine. And this mechanical energy can be directly used as the power to turbine, power to propeller of a ship, or it can drive a generator, and generator can convert the mechanical power to electrical power. So we will see the details of this in the next chapters, but this was aimed to tell you that these single stream devices are not usually used alone. They are mostly used as a part of an integrated system. So this was the end of this chapter. Now we will move to another chapter. Until now, we have learned about the first law of thermodynamics. The first law of thermodynamics deals with the conservation of energy. So the first law deals with conservation of energy, or quantity of energy. On the other hand, second law of thermodynamics deals with the quality of energy. So in this sense, it's a little bit more abstract than the first law, because we can directly see the results of first law by balancing the energy, but it's a little bit more difficult to understand the second law. Together with the second law, we will understand the concept of entropy. Entropy is a term used in thermodynamics as well as uh, social areas, but we will be using the meaning of entropy in thermodynamics. According to the second law of thermodynamics, the processes occur in certain direction, but not in any direction. What do we mean by this? For instance, heat moves from high temperature to low temperature and never in the opposite. Or electrical current moves from high voltage to low voltage. Or fluid flow, for instance, takes place from high pressure to low pressure. So any physical phenomenon is always from something high to something low. This is actually the statement of the second law. The processes, the thermal processes, occur in a direction which is from high temperature to low temperature. And also, by using the second law, we will be able to find out the maximum attainable work from a system. So we will be dealing with the factors that will affect the performance of a system or efficiency of a system, which are related to the second law of thermodynamics. So second law and the deductions from it: predicting the direction of the processes from high temperature to low temperature, establishing the conditions for equilibrium, because when for instance, temperatures become equal, we call it a thermal equilibrium. Determining the best theoretical performance of a cycle. So cycles cannot exceed a certain efficiency or certain performance due to the principles of second law of thermodynamics. Evaluating quantitative factors that affect the performance, additional factors related to second law, and also calculating the properties such as internal energy and enthalpy in terms of other properties such as temperature or specific heat. So there are some statements regarding the second law. First, we have to understand the concept of thermal reservoir. A thermal reservoir is a system with a constant temperature, and this temperature does not change if we add heat or if we remove heat from the system. For instance, the atmosphere or sea or a big lake is a thermal reservoir because you cannot change the temperature of atmosphere or a sea by adding heat or removing heat. So these kinds of systems with constant temperatures are called thermal reservoirs. There are two statements relating to second law. The first of the statements is Clausius statement. The second statement is Kelvin-Planck statement. According to Clausius statement, it's impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from cooler to hotter body. It means that if you want to move heat from a cooler body to hotter body, it's necessary to add some work. This is what happens inside the refrigerators. Inside the refrigerators, we have a cooler medium, and this cooler medium is maintained at colder temperatures, or sometimes the temperature is lowered, but it can be done only by adding work to the system. And this work is actually the compressor work. This is the statement of Clausius statement. The second statement and Clausius statement is related to refrigerators. And the second statement is called Kelvin-Planck statement. And according to Kelvin-Planck statement, it's not possible to convert all the energy, all the heat energy to work. So it says that some of the input energy must be rejected, otherwise the cycle cannot be completed. So this is used in heat engines. In a heat engine, only part of the energy can be converted to work. It's the statement of the Kelvin-Planck statement. In the Clausius statement, it says that it's not possible to transfer heat from a colder body to hotter body without addition of external energy, which is the power of the compressor in a refrigeration system. So, what is the reason of having an efficiency expected then according to the calculations? There are many factors that affect the efficiency of a system. They are called irreversibilities. Irreversibility or reversible process is a process that can be returned to initial state. For instance, think about a pendulum, a frictionless pendulum. In this frictionless pendulum, if there is no friction between the pendulum and the air, and if there is no friction at this location, pendulum and the air, and if there is no friction at this location, the motion of this pendulum will be indefinite, so it will move back and forth indefinitely. This kind of system is called a reversible system because it can be returned to their initial states because there are no irreversibilities. What are the types of irreversibilities we can see in thermodynamic systems? It can be heat transfer from the boundary of a system. It can be unstrained expansion. It can be spontaneous chemical reaction. It can be spontaneous mixing of matter. It can be friction, as in here. It can be electric current flow through a resistance. It can be magnetization or polarization with hysteresis, and it can be inelastic deformation. These are the types of irreversibilities we can see in physical systems, but we will be using irreversibilities as heat transfer and maybe friction, and that's all. And sometimes maybe unrestrained expansion. Other kinds of irreversibilities can be studied in other disciplines like chemical engineering, but in the mechanical engineering discipline, we will be using the irreversibilities as heat transfer, unstrained expansion, and friction. There are two types of irreversibilities. One type is internal, which occur within the system. The other is external, which occur between the system and the surrounding. If there are no irreversibilities internally and externally, we call the system totally reversible. So it can be internally reversible, but externally irreversible. If both the internal and external are reversible, we call the system reversible or sometimes totally reversible. In the calculation point of view, we sometimes may assume that system is reversible. For instance, in statics or mechanics, we may say that the mass is just a point, so it doesn't have a physical magnitude. It doesn't have a physical size, physical dimension. The pulleys are assumed to be frictionless. The beams are assumed to be rigid, and so on. So these are the assumptions of irreversibilities in mechanics. But in the case of thermodynamics, our irreversibilities may include no heat transfer on the boundary, no friction within the, for instance, turbine, and so forth. The Kelvin-Planck statement says that it's not possible to convert all the heat input, all the energy input to work. Otherwise, the cycle cannot be completed. So some of the heat added into the system must be rejected so that the cycle can be completed. This is an example of a heat engine, and it explains you the statement of uh, Kelvin-Planck statement. You can see that an heat input of Q is converted to partly work, and some part of it is rejected. Why is this rejection necessary? Because without this, it wouldn't be possible to complete the cycle. Remember the steam plant. In the steam plant, there was a pump, then a boiler, then turbine, then a condenser. In the boiler, we add heat, similar to this. In turbine, we obtain work. In condenser, we reject some heat, and also in pump, even though it's small, we add some work. So what would happen without the existence of this condenser? Without this condenser, the steam leaving the turbine would not be able to be transferred into the boiler. So in order to pump this fluid leaving the turbine to back to the boiler, it's necessary to condensate it. It's necessary to convert it to liquid. In order to convert it to liquid, it has to be cooled. So some heat must be lost, some heat must be rejected. Otherwise, it wouldn't be possible to complete the cycle. So without rejection some heat here, it's not possible to complete the cycle. So this is why we say that, according to Kelvin-Planck's statement, it's not possible to convert all the heat input as work output, because some of the heat must be rejected, otherwise the cycle cannot be completed. It means that no mechanical system, or no, let's say no thermal system, cannot have 100% efficiency. If it was possible to convert this heat completely to work, then the efficiency is output divided by input. If output was equal to input, or in other words, if the work obtained here was equal to Q in the upper reservoir, then you would have an efficiency of 100%. But in reality, this is not possible, because according to Clausius' statement, we have to reject some of the heat. And because of this, the efficiency in thermal systems is always less than 100%. So depending on the amount of heat lost at the cold reservoir, the efficiency of the system is always less than 100%. For instance, for a steam plant like this, you should expect an efficiency of 30% or so. A system without any irreversibilities is called a Carnot system. So a heat engine without any irreversibilities or reversible heat engine is called a Carnot heat engine. And similarly, a refrigeration system without any reversibilities is called a Carnot refrigeration system or reversible refrigeration system. We have some Carnot principles. According to Carnot principles, the thermal efficiency of an irreversible cycle, actual cycle, is always less than the thermal efficiency of a reversible cycle. So the highest efficiency belongs to the reversible cycle or Carnot cycle. All reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiencies. So if it's a Carnot cycle, if it's a Carnot heat engine, if it's a reversible cycle, then if the reservoir temperatures are the same, we always have the same efficiencies regardless of the type of the system. So as long as the temperatures of the reservoirs are the same and as long as they are reversible systems, their efficiencies are always the same. For the case of refrigerators, the objective is to remove heat from a colder space and to transfer it to warmer space. The objective of a heat engine is to obtain work by transferring heat from hot reservoir to cold reservoir. Meanwhile, work is obtained. This is the objective of a heat engine, whereas the objective of a refrigerator is to remove heat from colder space and to transfer it to a warmer space, and this can be possible only by adding work according to Clausius statement. So in Kelvin Planck statement, it says that it's not possible to convert all the input energy to work. And in Clausius statement, it says that it's not possible to remove heat from colder space without the addition of work. If the purpose of the system is to cool down the cold reservoir, for instance, you have air conditioner systems at home, and in the air conditioner system, you have two modes, cooling mode and heating mode. In the cooling mode, the objective of the system is cool down the space. So in this case, the performance of the system is obtained from the cooling purpose. So the performance of the system is always some output divided by input. In heat engines, we use the term efficiency, but in refrigerators, we do not use the term efficiency because efficiency is a value which is always less than 1, but the performance of a cooling system can be greater than 1, which is most of the time greater than 1. So if the system is used for cooling, then we use a performance factor for the system as the cooling of the cooling capacity of the system divided by the work added into the system. And if you look at the system, you can see that work is just the difference between the QH and Q low. So you can write the performance of the system as QC divided by W. QC is the cooling of the system if it's used as a cooler. So this is the cooling mode. On the other hand, if you are using the air conditioner for heater, meaning that instead of using the cooling function, if you're using the heating function, then your output will be heating instead of cooling. So whereas you use QC here, in the heating mode, you use heating. So in the heating mode, the performance is calculated differently. And actually, if you compare them, you will see that performance in heating mode is equal to performance in cooling mode plus 1. So you can check it yourself. There is a relationship between the heating mode and cooling mode. Heating performance is always higher than the cooling mode because of this calculation. In reversible systems, because in reversible cycles, the heat addition and heat removal processes are realizing at constant temperatures. That's why for reversible systems, we can use the ratio of the temperatures instead of ratio of the heats. So this is only valid for reversible systems. or Carnot systems. So when you use the ratio of the temperatures in place of the Qs, in place of the QH and QLOW, then you can write the efficiencies and uh, performances for heat engines, reversible heat engines, and reversible refrigerators, not in terms of Qs as done before, but in terms of temperatures. So as you can see, if it's a reversible heat engine, then you can calculate the efficiency of this reversible heat engine from 1 minus Tc divided by Th. And if it's a reversible refrigerator, or in other words, if it's a Carnot refrigerator, for cooling function, beta is calculated from Tc divided by Th minus Tc instead of Qc divided by Qh minus Qc. And similarly, if the system is used as heating, so this is for heating, and this one is for cooling. If it's a Carnot refrigerator used as a heater, then the performance of the system is calculated from the use of temperatures instead of heats added in the low temperature reservoir and removed from the high temperature reservoir. Okay, let's take a look at this example. It's an example of a heat engine. One inventor says that he has a heat engine that can produce 410 kilojoules with the addition of 1000 kilojoules, and the reservoirs are at 500 kelvins versus 300 kelvins. We are going to determine whether the statement of the inventor is correct or not. Remember that according to Kelvin-Planck statement, Clausius statement, no heat engine can have a higher efficiency than the efficiency of a reversible system. So we should start with the fact that efficiency of an actual system is always less than the efficiency of a reversible system, Carnot system. So we are going to check this. If it's not correct, then we should say that the inventor is wrong. So according to his statement, the engine gives you 400 kilojoules with respect to heat input of 1000. So if you calculate the efficiency, output divided by input, it's going to give you 41%. However, a reversible engine operating between 500 Kelvin and 300 Kelvin is going to have a efficiency of 40%. And according to the Carnot statements, this is not possible. And according to the Carnot statements, this is not possible because the inventor's engine has a higher efficiency than a Carnot engine, a reversible engine that's operated between the temperatures of 500 and 300. So the inventor is wrong. It's not possible to have a efficiency from an actual engine which is higher than the efficiency of a reversible engine. The second example belongs to a refrigerator. In this refrigerator, the cold reservoir is at minus 5 Celsius. This is inside the refrigerator. And the hot reservoir is at 20 Celsius, which can be kitchen, for instance. Let's assume that this is the kitchen, the back of the refrigerator, and this -5 is inside the refrigerator. And in order to remove heat from a colder reservoir to warmer reservoir, we have to add work to it. So the amount of work is also given. So it says that the cooling performance is 8,000 kilojoules per hour. The work addition is 3,200 kilojoules per hour. And it's asking the COP of the system. So we are going to find the beta of the system, which is the cooling capacity of the system divided by the input work. This is for the actual system. We can also calculate this for a reversible system. In actual system, we use the Qs, but in a reversible system, we can use the temperatures. So according to the calculation of coefficient of performance, beta, QC divided by W, it gives you a coefficient of performance of 2.5. But a reversible system operating between the given temperatures, which is -5 and +22, the calculation of coefficient of performance gives you something else. Be careful. Here, the temperatures must always be Kelvin. So you need to use the Kelvin temperatures in the calculation of coefficient of performance of a system. And as you can see, the coefficient of a reversible system is 9.9, which is okay because no actual system can have a higher coefficient of performance than a reversible system. So similar to the efficiencies, we can write that the coefficient of performance of an actual system is always less than the coefficient of performance of a reversible system, or in other words, Carnot system. Do you have any questions so far? Okay, I think we should stop here. We can continue next week. If you can, if you don't have any questions, I will stop at this page 13 and we will continue next week. Do you have any questions? Okay, so have a nice weekend. See you next week.